Here we go with the 12-2 notes. On the back of your 12-1 notes.
I need the... Do I just do that?
When you're absent, what are you supposed to do? Or just come see me in advance. Don't make me stop class to get you things that you should already have. Okay. All right. These are on the back of your 12-1 notes because I'm like all saving some paper and stuff. This is not full service. Get up. Oh, you're welcome. That's on the video now. Okay. I can do it way better than she can. Okay. Here we go. You've basically covered all of this before, so we're going to go through this kind of quickly. The thing that comes out front is called your leading coefficient. The highest exponent is the degree. Oh yeah. The number that comes at the very end without a variable is called a... Without a variable is a constant. Right? Variable means ever changing. Constant means nope, stays the same. All right. I'm just going to let you fill these in because you should know them. Degree is the largest exponent. EXP, OVS, exponent. The degree tells us how many turns the graph of the polynomial will have. We'll talk about that in just a moment. The leading coefficient is the number in front of the variable with the highest exponent. The leading coefficient will help determine the end behavior, which we'll talk more about in just a moment. Domain and range all should be pretty good with, right? Domain are the x values, range are the y values. And with polynomials, since they're all continuous, or meaning that you can draw them without picking up your pencil, right? There are no sharp turns or gaps in the graph. Our domain for all of these will be all real numbers. So if you put anything other than all real numbers on the domain for this test, I will mark it wrong and laugh. X. Like that. That was a preview of life to come. I know. Thank you. All right, but range is not going to be so easy. You're going to have to stop and think about range. If you have an odd degree, so odd numbers, 1, 3, 5, 7, 9, ... then their range will always be all real numbers. If you have even degree, 2, 4, 6, 8, 10, ... then it will have a restricted domain, and you've actually got to see how far down does it go, how far up does it go. Okay? You good with that? Here's a little note. The degree, like if you're just looking at the graph, degree is equal to the number of turns plus 1. Okay? The number of turns plus 1. Does everybody get a chance to copy that down? Mm-hmm. Yes. Okay, here we go. So let's zoom in here on example 1. First off, I mean, you've got prior knowledge here. What is example 1? What kind of function? It's a quadratic, so its equation is going to be roughly x squared. It's moved left a little bit, and it's moved down a little bit. But roughly, we know this to be the equation y equals x squared plus blah, blah, blah. Okay? So, we know that the degree of this one is 2. But Miss Cleveland, let's just play for a second that we didn't know that this was a quadratic. Okay? How many turns does this function have? 1. Basically what I do is I just count the number of maximums and minimums here. I have 1 minimum, so that means that it turned once. 1 plus 1 would give us a degree of 2. Does that make sense? The number of, how many turns does it have? 1. And I told you that the degree is equal to the turns plus 1. Okay? So it turned once. 1 plus 1 would give you a degree of 2. Yes? What is our domain? Yeah, buddy. Okay. Range. The degree here is even, so look at what we just said about even functions. Even degree polynomials will have a restricted range, so you've actually got to figure this one out. It always goes from least to greatest, so how far down does this go? -1, and is it going to touch -1? Yes, so we use a bracket. And how far up is it going to go?
Forever.
Forever, forever, ever. And we always use a parenthesis on infinities. It's Toto. Does that make some sense? Okay. Next one. Let's count our terms, i.e. let's count our maxes and minimums. Right, I've got 1 here, 1 here. So 2 plus 1, this is a degree 3. Well, Ms. Cleveland, I already knew that because I remember back to everything my teachers taught me in Algebra 1 and Algebra 2. And I know that this is a cubic function, x cubed, right? Uh-huh. As I see some glazed over eyes looking at it. What's our domain?
All real numbers.
Always all real numbers. This is an odd function, right? It's got an odd degree. How far down is it going to go? Forever. How far up is it going to go? Look, I wrote you a note here. Odd degree polynomials have a range of all real numbers. So as soon as you see that it's an odd degree, you can simply put all real numbers. You? Yeah. Ms. Cleveland, I also know what example 3 is because I paid attention in Algebra 2, but let's go over it just in case. Okay, count the numbers of maxes and mins. 1, 2, 3. So what's our degree? 4. It's always one more than the number of terms. What's my domain?
All real numbers.
Always. For polynomials, all real numbers. But here, this is an even degree, so I have to stop and think about what my range is. How far down does it go? It's going to touch -1, so I use a bracket. How far up is it going to go? Forever. Now, I promise that it's not always -1, comma, infinity. I now realize that there was an error in my ways. I should have changed that. Now I know. Please try examples 4 and 5. Alright, most people are starting to wind down here. If not, keep going. Doing this first one, or example 4, I see 1, 2, 3 different terms. So what degree is this? 4. And how by looking at the graph do I know that 4 is reasonable?
Because there's 3 and then you add 1.
Good. Okay, but look at this one over here that had an even degree, and this one that has an even degree, and this one that has an even degree. What do you notice that those all have in common? They're pointing in one direction. So if you have an even degree, both of the ends are going to be going in the same direction. They're either both going up or they're both going down. So that's reasonable to me. What do you notice about the odd one? They're going in opposite directions. So this seems reasonable to me that the degree would be a 4 here. Okay. Domain?
All real numbers.
You range?
8 to -.
No.
Flip it?
Flip it. Okay, it's always least to greatest. I'm so glad you made that mistake because it's going to be made often. So now we get to talk about it. Always least to greatest. How far down is this going? How high is it going?
8.
And it will touch 8, so make sure that there's a bracket. All right, this one reminds me of the roller coaster that I will be riding on Monday evening because I'm missing school Monday and Tuesday for a student council state conference. So I will not be here. I will be here only Wednesday next week because on Thursday I have curriculum writing. So sorry about your bad luck. And then Good Friday. Okay. So here, I automatically know that this is an odd degree. Looking at this graph, how do I know that it has an odd degree?
It's opposite direction.
Their ends are going in opposite directions. So here, 1, 2, 3, 4, 5, 6, plus 1. This is degree 7. Domain? All the time, boo. Range? It's odd. All real numbers. Make an assessment. That's okay. Right? We didn't do anything that was crazy there. I'm not going to crank it up. Today it stays pretty chill the whole day. Miss Cleveland, that's what you always say. All right, here we go. End behavior. So we've already started alluding to this idea of end behavior. What is this doing at the ends of the function? Are they both going the same way? Are they going in opposite directions? So I want you to think about if I were to zoom out on this function until I can see the ends of the function, what is each side doing? So end behavior describes the behavior of f of x. What is f of x? Y. So this is the output or y values. Okay, so we're trying to determine what are the y values doing for this function as we go in either direction in the x-axis. So this here is notation. This is really why we're bothering teaching you this. This notation is used all the time in calculus. So in English, this says, as x approaches infinity, f of x approaches blank. And you're going to have positive infinity or negative infinity. Okay? And as x approaches negative infinity, f of x approaches, and you're going to have either positive infinity or negative infinity there. Okay? Miss Cleveland, how do I know that? Just be cool, Focus Eagles, I'll help you. Okay? Flock of Seagulls is a movie reference, though. Does anybody know that movie? Easy there! Be cool, Flock of Seagulls.
Nemo?
Not Nemo. So far from Nemo. John Travolta, Samuel L. Jackson. Pulp Fiction. Very good. And he goes into the apartment and there's that kid laying on the couch and he jumps up. He's got a Flock of Seagulls haircut. Okay, good. Here we go. So let's read the instructions. Enter the following functions into your calculator and determine the end behavior. Identify whether the function is odd, even, and whether the leading coefficient is positive or negative. Get your calculators every day when you come in. Okay. Now, eventually, we're going to get to a point where we don't have to put these into our calculator to realize what they're doing. So everybody join me in y equals. And enter example 6 in there, please. 2x to the 5th plus 5x to the 4th minus x plus 3. And we were messing with the windows and stuff last time, so it might behoove you to zoom 6 it just to get your nice normal window. Alright, so I have my little sketch there, but I can't really tell what's happening. So, does anybody remember how to zoom out? Zoom 3, but when I hit zoom 3, nothing happens. You have to hit enter. Okay, so zoom 3, enter. Good kids are going to write that down because when you'll ask me next time, I'm going to be like, go look in your notes. You know, I will. Zoom out, zoom 3, enter. Well, Miss Cleveland, that's really blurry. That didn't really help me. This is a little trick I use sometimes. If I hit second zoom, I can actually turn my axes off, and so I can see the graph alone without all of that other stuff in the way. So that's what the function looks like if you zoom out to negative 40 to 40, negative 40 to 40. And so we've got a lot of stuff happening here, but one of the first things I notice is that this is an odd function and they're going in opposite directions. Nathaniel? Zoom 3, enter to zoom out. Then I turned off my axes by going second zoom. You don't have to do that, but I just wanted y'all to see a clear picture. I automatically see that this has an odd degree, right? We knew that because we put it in the highest x when it was a 5. But still, the ends of this are going in opposite directions, okay? So let's look at this language right here. Left end behavior. As x approaches negative infinity, so think about what that means for a moment. How would we approach negative infinity? Going to the left. So as we're riding along this function to the left, bless you, what is y doing? It's approaching positive infinity. So as x approaches negative infinity, f of x approaches positive infinity. You could put y, but just infinity. The positive is understood as long as you don't put a negative.
So that's just positive infinity, correct?
Yes, or just infinity. Okay. Over here, what does right in behavior mean? As x approaches positive infinity, it means we're going to the right. So as we're writing this function and going to the right, what is happening to our y value? It is approaching negative infinity. So as x approaches infinity, f of x approaches negative infinity. Does that make some sense?
Yes.
I love when I make sense. No? Okay. Do y'all ever go back and watch these videos and y'all are like, what's happening in the class at that moment? Okay.
The one that I watched last night wasn't that bad.
Okay, because I did that one all by myself yesterday morning, right before I proctored the STAR test, so
Okay.
I was loving my life, and there was nobody else in here. Yes, sir?
That seems redundant. Why do we do that?
Because in just a moment, it'll be important to see what's happening to just the ends of the function. So as we're going to the left, it's getting bigger. As we're going to the right, it's getting smaller. That's really all that's saying in English. Okay, what happens if we didn't have the equation and we just had this? We could kind of reconstruct the function knowing that notation. Okay, is the degree even or odd? Odd, like Miss Cleveland. And is our leading coefficient positive or negative?
Negative.
Yeah, it is. So let's look at this for just a moment. The leading coefficient is negative. So that means as x is positive, y is negative. That's what the leading coefficient means. Okay? On the positive side of the function, it's going down.
Is there a way to look at that via the equation itself instead of, like, is it just a negative sign in front of that too?
It is. Yes. So here, I am going to argue we don't need to graph any more of these. This is my argument. Okay? My leading coefficient is positive or negative? Negative. And is my degree even or odd? Even. So let's stop and think about what that means for a minute. If it is even, what does that mean about the two ends of my function? They're either both going up or they're both going down. Okay? Well, if my leading coefficient is negative, they're both going down. So think about this. This graph looks something like this. There might be some twists and turns in there, but at the end of the day, the left side's going down, the right side's going down. So as x approaches negative infinity, what's happening to my y values? They're approaching negative infinity. And as we approach positive infinity, what's happening to y? Negative infinity. So now that you know a little bit about the purpose of the degree and the purpose of the leading coefficient, you don't even need your calculator anymore. Isn't that dandy? Okay, let's do one more. My leading coefficient is positive, and my degree is odd. So positive leading coefficient, does that mean that the right side is going up or down? Up, because it's positive. So odd functions, what happens in an odd degree function? The ends go opposite direction. So if it's a positive lead coefficient, it's up in the positive direction. So it doesn't matter what happens in between. The left side's going down, the right side's going up. So as we approach negative infinity, f of x approaches negative infinity. And as we approach positive infinity, the right side approaches positive infinity. Oh, yeah. I would like for you to try the next one all by yourself. Do you need a musical interlude while you do that? All by yourself.
Can you do a wonderful world?
What a wonderful world. Is that what you needed? Yeah? Okay. Apparently so. Okay. Clouds of gray. That wasn't good. Okay. I'll work on it. Y'all are going to miss this class. She said, hopefully. Okay, so, leading coefficient, positive or negative? Well, Ms. Cleveland, I don't see anything in front of the x to the 6th. What does that mean? It's a positive 1. And what is the highest exponent? 6, so it is even. Even functions, what happens to the ends of their function? They go the same way. So in this one, they're both going up or they're both going down. And since this is a positive lead coefficient, it looks something like this, right? Who cares what's actually happening in between? It could twist and turn and do all of that mess. But what's important is that the ends are both going in the same direction and in the positive direction. So in both cases, these are approaching a positive infinity. Basically, everything I just said happens in these boxes here. So I'm going to let you read these for your own leisurely reading pleasure. Okay, it kind of summarizes everything that I just said verbally into a written format. So I do encourage you to go back and read those. I want you to try number 10. I don't want you to graph it in your calculator. I just want you to think through it, right? We have a degree of 120, but even that you should be able to think about what your leading coefficient is and what your degree is and be able to tell me what the end behavior of this function will be. I'll give you a moment. Alright, so what's happening here? Well, the leading coefficient is negative, and the degree is even. What do we know about even functions? Same direction. And because our leading coefficient is negative, which way are these going? Down. So it's going to look something like this, right? I don't know how many twists and turns are in the middle, but the ends are both going down. So as as x approaches a positive or negative infinity, f of x approaches a negative infinity. Right? It doesn't matter which direction we're going. As x goes way far out to the left, as it goes way far out to the right, they're both going in the same direction. In English, both sides are going down. It's going down for real. No. Okay. Got a few Snickers out of hard to snicker people. Okay. Zeros. What do I mean when I say zeros? X-intercepts. There are two alternative words for zeros and x-intercepts. What are they? Solutions. I think I might have heard it. Roots. Very good. Just to make this a very complicated process, we have 4 different words that mean roughly the same thing. Just for fun. For a polynomial function f of degree n, so maybe of degree 2 or of degree 5, of degree n, okay, it has some exponent, that's a number. The function f has at most n real roots. What? Okay, so quadratic is y equals x squared. How many times is the maximum that it will touch the x-axis? Twice. X to the third, n is 3. How many times maximum will it touch the x-axis? So on and so forth. So that function up there, x to the 120th power, it will touch the x-axis at most 120 times. Okay? But let's stop and think for really quickly. I'm going to do this down here. The equation y equals x squared. Okay? Maybe we multiply it by something, maybe we move it up or down, maybe we move it left or right. But you've got 3 scenarios. It can touch a maximum of 2 times, like it's supposed to. Can it ever touch more than 2 times? Not if it's quadratic. It can touch once, right, where it just bounces right off that x-axis and it only touches at that point where it bounces. Or it can be like, no, I'm good. And not touch the x-axis at all, right? So when I say at most, think through these other options, right? It can touch less than that, but at most it will touch n times. So sometimes a 0 doesn't actually cross the x-axis, but just touches it. Okay, that's what I was saying down here. And that's what we call a root of multiplicity. Do you remember hearing that in the past?
No.
Okay. Great. When it just bounces off the x-axis, that almost kind of counts as 2 roots. Okay, it eats up some of your other places that you're going to touch the x-axis. Okay. So looking at these examples, the maximum number of zeros, that one's super easy. What's the degree of number 11? So what's the maximum number of zeros it'll have? 5. What's the degree of 12? How many zeros can it have? Oh, 4. What's the degree of 13? What's the maximum number of times it's going to cross the x-axis? Miss Cleveland, this is really easy. Make a whole test this. And what is the maximum number of zeros for number 14? Yeah, it is. Wait, Miss Cleveland, you got it. So I was going to say 2. Okay. But we need to find the actual real zero. So let's go ahead and graph number 11. It should be the last function that you put into your, what do we call this? Calculator, actually. It's the same functions from above. Now we're finding the zeros. So when I graph this, I am going to go back to Zoom 6. And I'm going to go turn my axes back on. Okay. So here we go. Let's just think through this really quickly. It can have a maximum of 5 times touching the x-axis, but we've got 1, 2, 3, and then it's supposed to go back up. If it went back down, I think we'd see it here, right? We can zoom out and see that it never comes back down again. Another place that you can go look is in the table. Look, as we go out, what's happening to these numbers? They're getting huge. That's not coming back down, okay? So when we go look at this, I can't really tell where that is. Can you? Somewhere between 2 and 3. Do you remember the functions on your calculator to find the exact zero? Second, trace 2. Good kids are going to write that down. Second, trace 2. The zeros. Second trace 2 is how you find the zeros. Now, I want you to read what your calculator is saying to you. Left bound. What does that mean? Well, it wants you to tell it a number to the left of that function. So, everybody, lightly put your pencil on the 0. Don't draw on the screen, please. What is a number to the left of where my pencil is? Negative 1 definitely is, but let's get closer. I'd say 1 or 2 would be a good guess. I'm going to say 2. And as soon as you enter that, you should have a left arrow come up. Now, what is a number to the right of my pencil? 3 or 4. Now, when you check, is that 0 in between those 2 little arrows that you made? Yes, hit enter. And we're at 2.5. Okay, what is this mess over here? What does e to the negative 12 mean?
There's 12 more zeros. on
There's 12 zeros in front of it, so what is your calculator actually telling you there? It's, if you move your decimal place over to the left 12 places, that number is getting ridiculously small, so that actually just means 0. So you have a 0 at x equals 2.5. Yes? So how did we find zeros in our calculator? Second trace 2. Let's go put the next one in our calculator. Negative x to the 4th plus 5x squared minus 4 graph. Oh yeah. It looks like I have zeros at negative 2, negative 1, 1, and 2, but it, you know, my eyes could just be faking me out. I don't know. What's a good way that I could check this for certain? I could do second trace 2, but there's an easier way. Let's go to our table. Look, if I go to negative 2, look, it's a 0. Boom. What about negative 1? Oh, yes. Ooh, 1, 0. Oh, yeah, look at that. There's all my zeros right there. Right, because you're wanting the y value to be 0. And what's the maximum number of zeros I can have? 4. I just found 4 of them. I know I have the maximum amount. So I'm going to be convenience-oriented, not lazy. Plus or minus 1 and plus or minus 2. What does that actually mean?
Negative 1, negative 2.
Negative 1, negative 2, positive 1, positive 2. Okay.
We accept both, right?
Huh?
We accept both?
Yes. Yes. Are we all good with this concept? Okay, then I'm just going to leave it there. And then now what I want you to do, you should be able to go back and complete the rest of your homework assignment. Okay, so this is the assignment you should have picked up last time. Okay, on the top portion, you are doing what you learned on your 12-1 notes for all of these graphs. Now today you can go back in and fill in the domain, the range, end behaviors, and zeros. Okay, so that's what you're doing for the remainder of the period. Questions before we get started? Yes. Okay, get started. Extras are up here on the podium.